In this lecture, we are looking at quadratic forms of normally distributed variates. In the previous lecture, we looked at the sampling distributions of mu and sigma. It's important to look at the sampling distributions of these estimators because these two parameters uniquely characterizes the multivariate normal distribution. If we know mu and we know sigma, we kind of know everything there is to know about our multivariate normality. So the quadratic forms kind of follows organically from this because the idea of a quadratic form comes in all forms and shapes throughout our inferential journey. Inferential because we want to estimate mu, we want to estimate sigma. We need to know what these values look like, especially when they come, of course, from a data matrix or from data. So we are going to look briefly at quadratic forms of normally distributed variates. The objectives here is to understand, know, prove and apply lemmas 2 and 4. We want to understand, know and apply lemma 3. And we'd like to motivate and discuss corollaries emanating from these lemmas as well. In lemma 2, let X be a p by 1 vector which is standard multivariate normally distributed. I have a matrix A. This matrix A is square, p by p. It must also be symmetric. And in this case, we assume it's idempotent of rank R. In this case, of course, R must be less than or equal to p. Then, the quadratic form S, X transpose AX. This is my quadratic form. X transpose AX will have a chi-square distribution with R degrees of freedom. Now, I would like you to go, that's my mistake, sorry. I would like you now to go and say, hang on, chi-square is univariate. So does this mean a quadratic form is univariate? Well, in our case, yes. This specific S that we have over here, this S, is univariate. And thus it has a univariate distribution. Before we prove this lemma, let's just answer some brief questions. What exactly is the dimension of S? Well, we just said it's univariate. If it's univariate, it means it's 1 by 1. Let's verify that. 1 by 1. X transpose is 1 by P. A, we saw, is P by P. And X, we saw, is P by 1. So, of course, this means these have to correspond, these have to correspond, and these at the outer edges will be what we are left with. Actually, not what I wanted to do. My apologies. There's a 1, there's a 1. And this is where this 1 by 1 comes from. So immediately we can confirm that S is indeed a scalar. We have to remind ourselves about the behavior of A. It's symmetrical and idempotent. You can make a note here already halfway through that when A is specifically the identity matrix, which is of full rank, that we then have our, for lack of better description, our full chi-square distribution up to P with P degrees of freedom. More on that in a minute or 3. So now, lemma 2 defines our quadratic form. S, X squared, or rather, X transpose AX. Which begs the question, okay, let's go back to what we've learned before. Is there a univariate consideration or something close enough to the univariate consideration which might be valuable for us to take note of? Well, fortunately, yes. In Bain and Engelhardt, many moons ago, we had a theorem 835. This theorem told us if Z is standard normal, then Z squared will be chi-square with 1 degree of freedom. Maybe you can recall this. If not, please go and visit that theorem again. Okay, but how exactly does this now relate to lemma 2? Well, let's just think about what we already have here in corollary 10. X transpose X, if I write this down, X transpose X, this means I have X1 up to XP times X1 up to XP, right? And if I multiply these out, I'm going to be left with X1 squared plus X2 squared plus all the rest plus XP squared. But if X comes from a standard normal, or in our case standard multivariate normal, this means that I'm taking the square of a standard normal variable and I'm adding them together. And in another section in our work on the second year level, this is corollary 832, we know that the sum of standard normal variables, or rather the sum of chi-square variables or independent chi-square variables, again follow a chi-square distribution. So each of these can be viewed as chi-square 1 by themselves. And now we're adding all of them together. They are independent, by the way, because of our identity covariance assumption in this case. So when we now go and we say, okay, let's see this quadratic form. That A matrix is kind of like our generalizer in a sense. If we make it identical or identity matrix, we end up with our results from the past. But because we're working with vectors and not just single values or single variates, we kind of have to allow for whatever other things might happen in between. Other things might happen in between can be characterized by this symmetric and idempotent matrix A. So let's prove this. H is some orthogonal vector such that H transpose AH is an IR0, 0, 0 matrix. Take note specifically that that R over there corresponds to the rank of A. Now we build an auxiliary variable. Let's call this auxiliary variable Y. Y will still be multivariate normally distributed. And we can now go and say, that's my definition of my quadratic form. I know that I can write each x now in terms of h and y. And then we kind of kick back and we say, but hold on. Over there, we have our orthogonal construction. In this case, I must then have the sum up to r, that r, of the y values that we have. But the y values are multivariate normally distributed. Even though y is p-variate, I'm only going to be using the first r of them because of this construction that I have over there. Let me put another purple block around it. So we're only going to be using the first r, and that is why we have that sum up to r over there. But the yi's are standard normal. The yi squares are chi-square 1, and we sum them up to r. So we have a chi-square distribution with r degrees of freedom. Now example 16 asks us specifically, write down S when P is equal to 2 and A is equal to A, B, C, D. There is a typo in the notes, so please change that C to a B because it has to be symmetric, of course. All right? Let's write this out here very, very briefly. I have S, which is X transpose AX, right? And what would this be equal to? Well, X1, X2, I have A, B, B, C. Is that what I had? Let me just make sure. I'm confused now. A, B, C, D. Let's make that A, B, B, C. That should be fine. Let's hold thumbs. I don't mess this up. And here I have X1 and X2. So if I now go and simplify this, I will end up, you can go and confirm the steps in between. I end up with an x1 squared a plus 2x1 x2 b plus x2 squared c. So just specifically, I'm going to reiterate here, this is for the p equals 2 case, right? Already now we can see there is definitely some quadratic something going on here. It reminds me always very briefly of, when you want to expand a double term like that, it's always a squared plus or minus 2 times the first one times the second one plus the last one squared. So it looks almost very similar to that idea, except that we have now kind of extended this into the vector space using x from a multivariate normal and a, which is some matrix. Some matrix which gives us access to this generalization for some values of a, b, and c. Now, for example, if you make a equal to 1, and c equal to 1 and b equal to 0, then we just have x1 squared plus x2 squared. And x1 squared plus x2 squared in this case will be chi-square 2 distributed. So all of this kind of immediately makes sense. And now we can see, but okay, I kind of have control over what will happen to s if I use this kind of arbitrary a, which gives me access to even more things. Something that you can go and do is you can go and write this out. What would this look like for p equal to 3? Just make up a matrix with constants like I did now, which adheres to symmetry and idempotency, or not. It's not an essential aspect of this. And have a look at what that quadratic form in itself would look like. Corollary number 10, we've looked at now. We know why that chi-square will be up to p. We've investigated that. For corollary 10.2, I'm going to give that over to you to go and dream a little bit about. In short, we basically have some n by 1 vector. Then we're just showing that n minus 1 times s squared will give me its own chi-square distribution again. Immediately, we're kind of starting to touch again on sampling distributions of certain functions of my data matrix or of my x vector. And that's kind of what we want to use this for. Lemma 3, x is again a standard normal vector, multivariate normal vector. Then it's given that I do have some quadratic form S. A is positive definite, or at least positive semi-definite. And Y is some matrix B times X for some B. If B times A is equal to 0, then S and Y are independent. We're going to use this as a general form in order to address some other aspects that might come up in our inferential life. So this is a very generic kind of lemma, but it remains extremely useful. We will see why in corollary 11. If x is a standard normal vector, or multivariate normal vector, then x bar and s squared are independent. Who cares? Well, Johan cares. I think you should also care. The reason why x bar and s squared should be independent, because they are used in this case to look at ways in which we relate these back to our sampling distributions or our estimators of mu and sigma. I would like x bar and s squared to be independent, because then I do not have any muddy water in the estimation, if that makes sense. I want you to know that it's also not so obvious that these things are independent, because that s squared contains X bar. So this is not necessarily so obvious, but it is true. At first glance, you would not know. And that is why lemma 3 helps us to understand and motivate corollary 11 in this case. Now, when we look for any x coming from a multivariate normal sample or distribution with mean mu and covariance sigma, then my quadratic form is actually x minus mu transpose sigma inverse x minus mu. And that S has a chi-square distribution with p degrees of freedom. You can go and have a look. I'm going to draw little glasses. You can go and have a look here. Those are your eyes. You're looking. Why exactly that is true. Remember here, of course, that sigma minus a half is, of course, the same as sigma inverse. This is very useful because that S in lemma 4, the S in lemma 4, is actually what we have also in the likelihood function, or at least in the density function of the multivariate normal. So everything we've discussed up to now is rather general or rather generic. But we reach a point in lemma 4 where we realize, okay, but hang on, we've built all this prior knowledge now through lemma 2, through corollary 10, through lemma 3, through corollary 11, that we now can identify what we've been having all this time in a very quick and painless fashion. So that is specifically why this is useful. We know how this S works. Out of pure interest, this S in many times or many cases is something called the Mahalanobis distance. For those of you going into mathematics, applied mathematics, financial mathematics, statistics, mathematical statistics, data science, distance measures are very important because this gives us an idea of how far apart is x and mu. If x is far apart from mu, it means that my observation is centered far away from the mean in whatever space, p-variate space we are working with. So that's just a short note that is also something called the Mahalanobis distance. Then we have some corollaries that follow from this that I want you to go and look through. This reminds me specifically of theorem 836 in Bain and Engelhardt. It's a very infamous theorem in WST 221, known to be quite long. But there we also show the independence of x bar and s squared. And in this case, this is exactly what we use these lemmas for. We go and show x bar and the components of s squared are independent. And if they are independent, it means that I can estimate them individually as if they are living and breathing by themselves. This is not always the case in many other multivariate environments. Not even in all the univariate environments this is true. If you only have positive data, let's say for example, number of claims, then you might be working with a Poisson distribution which only has one parameter. If you're working with something else like an extended Poisson or a generalized hypergeometric or something to that effect, distribution which has more than one parameter, the parameters might be very intricately involved in each other. And if you do not have this independence, it really makes the estimation quite difficult. You have to rely on iterative procedures, becomes computer heavy. But in the multivariate normal case, these observations, or rather these estimators, gives us access to this wonderful idea of independence, and we can show that using the lemmas that we've covered today. In the next lecture, we're going to be looking at Hotelling's t-squared, which I find a very nice section of the work because it gives us time to briefly reflect on some theory, but then it gives us some inferential insight into determining or testing hypotheses about inferences and stuff about multivariate means. So that is what we will be looking at next.